In the middle of the ocean, there is a fish that carries a sword. Not a metaphorical sword, nor is it a pointed snout that people call a sword simply because it resembles one. It is a real, flat blade made of dense bone, sharpened on both edges. It extends forward from its skull like a weapon mounted on the bow of a biological submarine. And here's the first mistake everyone makes about this. The swordfish doesn't use the blade to stab. If it swung the blade, it would kill itself. Colliding head-on at 30 miles per hour transmits the impact force through the blade and skull directly to the brain. This is equivalent to driving a car into a concrete wall. Every time a swordfish strikes, it inflicts a concussion on itself. The brain, the most delicate organ in its body, bleeds as a result of its own weapon. Instead, the swordfish does something far more sophisticated. It slashes. It swings its massive head side to side with extraordinary velocity, sweeping the blade laterally through schools of fish like a scythe cutting through a field of wheat. The prey are not impaled. They are stunned by the kinetic energy of the swing, physically cut by the razor edges of the bill, or simply caught in the hydraulic turbulence of a 1-meter blade moving at lethal speed through dense water. They become easy meals. Floating, disoriented, some of them already dead from the impact before the swordfish circles back to eat them. This is not a spear, this is a sword. The animal is correctly named, and the weapon itself is one of the most remarkable structures in vertebrate biology. But the blade is just the beginning, because the swordfish doesn't use this weapon on a sunny reef at 10 meters depth where any predator could operate. It uses it in a place that no other billfish on Earth is willing to go. Straight down, into the dark, into the cold, into water that would crush a car and freeze a mammal and blind anything that doesn't carry its own heating system inside its skull. The sailfish is faster. The marlin is stronger. Neither of them goes where the swordfish goes. And what the swordfish does down there, every single day, is one of the most extreme biological performances on the planet. Every morning, when the sun's rays illuminate the water's surface, the swordfish does the exact opposite of what logic would suggest. It leaves that spot. It dives downward, initiating a vertical migration that takes it hundreds, sometimes thousands of feet deep into the mesopelagic zone, the twilight zone, where sunlight transitions from pale blue to complete darkness. Based on data scientists have gathered from free-swimming swordfish over the past several decades, these animals regularly dive to depths of 1,600 to 3,000 feet throughout the day. Some individuals have been recorded at depths exceeding 5,000 feet. 5,000 feet, nearly a mile below the surface. At this depth, water temperature drops below 5 degrees Celsius, cold enough to slow down all chemical reactions in a cold-blooded body. The pressure exceeds 160 atmospheres. That's 160 times the pressure at the surface. A force exerting enough pressure on every square centimeter of the animal's body to flatten a steel barrel. And the swordfish is not a small animal. A mature adult weighs over 450 kilograms, half a ton of muscle, bone, and organ tissue descending daily into conditions that should shut down every system it has. Why? Why would any animal put itself through this? Because that is where the food is. The deep scattering layer, a massive aggregation of squid, lanternfish, and crustaceans, migrates downward during the day to avoid visual predators at the surface. The entire prey base of the open ocean drops into the twilight zone every morning like an elevator descending into a basement. Most surface predators watch it go and wait for it to come back up at night. The swordfish follows it down. The prey it's hunting is not ordinary surface fish. Down here, the targets are different. Dosidicus gigas, the Humboldt squid, aggressive, pack-hunting cephalopods with razor-lined suckers. Lampernictus, lanternfish that produce faint bioluminescent glows along their bellies, tiny but nutritious and present in enormous numbers. Paralepis, barracuda, elongated ambush predators of the twilight zone with translucent bodies and needle teeth. The swordfish eats all of them. It is not selective. It is efficient. Whatever moves in the twilight zone and fits inside the lethal arc of the blade becomes food. And down here, with the cold slowing every other predator to a crawl, the swordfish has the entire buffet to itself. It follows its food into the dark, into the cold, into the crushing pressure, because it is the only billfish on Earth that can function down there. The sailfish cannot. The marlin cannot. Their muscles seize in the cold. Their vision fails in the dark. Their reflexes slow to uselessness. The swordfish descends into an environment that disables every competitor and hunts alone in a zone where it is the only predator fast enough and warm enough to catch anything. But to make that possible, to operate a half-ton cold-blooded body in water that should paralyze it, the swordfish carries a piece of biological engineering hidden behind its eyes that has no equivalent anywhere else in the animal kingdom. The problem with cold water isn't the cold itself. The problem is the effect the cold has on the nerves. Nerve signals are electrochemical stimuli. They depend on ion channels in cell membranes that open and close at specific rates. In warm water, these channels fire rapidly. Reflexes are quick. Vision becomes sharper. Muscle reaction times are very high. In cold water, however, chemical processes slow down. Ion channels become sluggish. Nerves function at speeds far below normal. For a cold-blooded fish, a drop in temperature from 25 degrees to 5 degrees does more than just cause discomfort. It renders the fish functionally blind and neurologically impaired. Reaction time increases. Visual processing is disrupted. The animal becomes slow, sluggish, and defenseless. The swordfish solved this problem by building an oven inside its own head. Behind the swordfish's enormous eyes, the size of a basketball, among the largest eyes of any fish, lies a block of modified muscle tissue known as a heat-producing organ. This tissue was once a standard extraocular muscle, the kind that moves the eyeball within its socket. Evolution took this tissue, stripped it of its ability to contract, and transformed every cell into a specialized heat generator. The heater organ is packed with mitochondria, the organelles that produce cellular energy, at a density that far exceeds any normal muscle tissue. These mitochondria are essentially running at maximum capacity around the clock, burning fuel not to produce movement, but to produce pure thermal energy. The organ generates heat the way a furnace generates heat, by burning everything as fast as possible and radiating the result. But generating heat in cold water is useless if the heat immediately escapes. Blood flowing to the eyes would cool down before it arrived if it traveled through the freezing tissue surrounding it. The swordfish solved this with a countercurrent heat exchange system, a network of arteries and veins running alongside each other in opposite directions. Warm blood heading toward the eyes passes directly alongside cold blood returning from the eyes. The heat transfers from the outgoing warm blood to the incoming cold blood before it can escape into the surrounding tissue. The system creates a thermal barrier. The eyes and the brain behind them are maintained at temperatures up to 30 degrees Celsius above the surrounding water. 30 degrees. The ocean around the swordfish is at 5 degrees. The brain inside its skull is operating at 35, the same temperature as your brain, in water that would give you hypothermia in minutes. The result is devastating. At 5,000 feet, every other fish in the water column is neurologically impaired. Their retinas are processing visual information at a fraction of normal speed. Their reflexes are sluggish. Their muscles are firing in slow motion. The swordfish's retina is operating at full tropical speed. Its muscles are firing at surface-level rates. Its brain is computing at the same frequency as if it were hunting in warm Caribbean water. A warm-eyed predator in a room full of cold, blind prey. a soldier with thermal imaging in a field of opponents who can barely see. The swordfish doesn't just survive the deep, it has turned the deep into a private hunting ground where the cold itself is its greatest competitive advantage. The presence of a heat-generating organ is a massive advantage. It's like the difference between a top-tier predator and a helpless prey. Researchers studying captured swordfish have measured this difference. When the heat-generating organ is experimentally disabled, the animal's reaction time quadruples within minutes. Visual processing speed plummets. A sideways attack that normally takes milliseconds becomes clumsy and inaccurate. A swordfish without a heat-sensing organ is defenseless. It is a half-ton mass of cold muscle carrying a useless sword in the dark. No faster or more skilled than the other fish at that depth. Heat generators are the entirety of its competitive advantage. Without them, the swordfish is nothing more than another cold body sinking in the void. But keeping a heat generator running inside its skull for 24 hours comes at a cost. And the swordfish pays that cost every second of its life. To understand what the swordfish is, you need to see what it was. And what it was makes the modern version even more unsettling. 60 million years ago, shortly after the extinction of the dinosaurs, the ancestors of the swordfish looked nothing like the animal we know today. They had two bills, both the upper and lower jaws projected forwards simultaneously, creating a double-bladed structure that resembled the beak of a modern needlefish. 2 points, 2 blades, a symmetrical weapon that looked like it should work, and didn't work well enough. Over tens of millions of years, evolution ran the experiment. The lower jaw gradually shortened, receded, disappeared entirely. The upper jaw elongated, flattened, and sharpened. 2 blades became 1. Symmetry was abandoned in favor of specialization. The single blade was more hydrodynamically efficient, generated more lateral cutting force, and created less drag during high-speed swimming. Evolution had tried a symmetrical design, measured its performance, and concluded that asymmetry was superior. But the transformation doesn't stop at the species level. It happens within each individual swordfish during its own lifetime. A newborn swordfish is tiny, small enough to sit on a human fingertip. It looks like a normal bony fish. It has scales covering its body. It has teeth in its jaws. It has a proportional head. It looks like nothing special, a generic larva in a sea of generic larvae. Then it begins to change. The scales disappear, every single one of them shed over the first year of life. The adult swordfish has no scales. Its skin is smooth and bare, reducing hydrodynamic drag to an absolute minimum. The teeth vanish next, slowly absorbed back into the jaw as the bill elongates and takes over every function the teeth once served. A swordfish is born with teeth and dies without them. Born with scales and dies smooth. Born with a short face and dies carrying a meter-long blade of reinforced bone. Every swordfish undergoes a personal transformation from an ordinary fish into the open ocean's most expert predator. Tooth loss is particularly revealing in this regard. Most predatory fish retain their teeth throughout their lives. Teeth are weapons. Teeth are tools. Teeth are essential for any predator that hunts with its jaws. The swordfish, however, has no need for them. Its beak has completely replaced the teeth. The side-cutting technique requires no teeth. It performs the cut with the edge of its sword. It then swallows the stunned prey whole. Teeth have become a useless burden. In an animal that kills with a bony sword and consumes its crippled prey by sucking it in, they are structurally costly and serve no function. That is why the swordfish eliminated them. Just as the frogfish eliminated its swim bladder, just as deep-sea fish eliminated their eyes because they live in constant darkness. Evolution doesn't hold on to what it doesn't use. The swordfish abandoned its teeth, scales, and traditional head shape in exchange for the most efficient open ocean hunting system in the pelagic zone. A biological upgrade from a prototype to a fully functional weapon system. And this finished weapon is made of materials that would make a structural engineer envious. The swordfish swings its sword in dense water at speeds that exert immense mechanical pressure on its beak structure. Thousands of strikes over its lifetime. Each strike sends shock waves generated by kinetic energy back through the bone to the skull and the brain inside. If the beak were made of a single, dense type of bone, like a human femur, it would either shatter from the repeated impacts or transmit lethal shock waves to the brain with every swing. But the beak does neither, because it is built on a material gradient unlike anything else in vertebrate biology. At the very tip of the beak, the first point of contact with the prey, the bone is extremely dense. It is heavily mineralized with calcium phosphate, hard, compact, designed to transmit maximum force to the target. The tip strikes like a hammerhead. However, as the bone structure extends backward from the tip toward the skull, the internal architecture changes. Density decreases, porosity increases. The hard mineral matrix gives way to a softer, more compliant structure filled with microscopic voids and flexible collagen fibers. The bone becomes a shock absorber. The kinetic energy entering the tip as a sharp mechanical impact is gradually dampened, dispersed, and dissipated as it passes through the increasingly porous structure. By the time the remaining energy reaches the skull, it has been reduced to a level that the brain can tolerate. Dense at the tip, porous at the base, hard where it hits, soft where it connects to the head. The bill is not a uniform weapon. It is a graded energy management system that delivers force outward and absorbs force inward. A car's crumple zone works on the same principle, rigid at the passenger cabin, deformable at the bumper. The swordfish invented the crumple zone 60 million years before humans built the first automobile. And the gradient isn't simple. It's not a binary switch from hard to soft. It's a continuous, smooth transition across the entire length of the bill. Micro-CT scans of swordfish rostra reveal that the bone density changes incrementally, almost pixel by pixel along the length. There is no abrupt boundary where dense bone becomes porous bone. The transition is seamless. Modern composite engineers call this a functionally graded material, a structure where the properties change continuously rather than in discrete layers. It is the holy grail of material science. The swordfish has been manufacturing it biologically for 60 million years. Human engineers achieved it in the laboratory approximately 15 years ago. But there is a second layer to this engineering that makes the swordfish bill genuinely unique in vertebrate anatomy. The bone is acellular. In almost every other vertebrate on Earth, bone contains osteocytes, living bone cells embedded in the mineral matrix that act as sensors. They detect microcracks, signal repair mechanisms, and coordinate the remodeling of damaged bone through centralized biological control. It is a managed repair system, like a maintenance crew that inspects the structure, reports damage, and dispatches repair teams. The swordfish discarded this system. Its bone has no osteocytes, no centralized damage detection, no managed repair crew. Instead, it uses a decentralized network of osteoclasts and osteoblasts, cells that resorb damaged bone and form new bone, operate autonomously across the entire surface of the beak without a central command. The weapon heals itself, on autopilot, continuously. Microcracks caused by repeated impacts are automatically repaired before they lead to structural damage. A self-healing blade. It is made of a material that gradually absorbs its own shock waves. It operates with a regional autonomous repair system that functions continuously without neural input. It is not the swordfish that maintains its weapon. The weapon maintains itself. And it needs to, because the things the swordfish encounters in the depths are not small. and they do not surrender quietly. At 3,000 feet, in water so dark that the swordfish's heated eyes are the only functional visual system in the entire water column, the swordfish encounters something that fights back. The giant squid, Architeuthis ducks. 10 meters of tentacle and mantle armed with suckers ringed in razor-sharp serrated teeth. Eyes the size of dinner plates, the largest eyes in the animal kingdom, evolved to detect the faintest bioluminescent flicker in absolute darkness. This is not prey that holds still and waits to be slashed. This is prey that sees you coming, grabs you, and tries to pull you into its beak. We have never filmed this encounter, not once. The battles happen a mile below the surface in total darkness, but the evidence is carved permanently into the swordfish's body. Circular scars, perfect rings left by giant squid suckers on the swordfish's skin. Each scar a record of a fight. Each fight conducted at extreme depth in freezing water in absolute blackness between two animals that can barely be called the same category of life. A vertebrate and an invertebrate, a blade and a tentacle, warm eyes and cold blood. The swordfish cannot overwhelm a giant squid with mass the way a sperm whale does. It weighs half a ton. The squid can weigh nearly as much. Instead, the swordfish relies on the one advantage that no other deep water predator possesses at this depth: speed and heated neurology. Its brain is warm, its reflexes are fast, its muscles are firing at surface temperatures. The squid's nervous system, despite its enormous eyes, is operating in cold water. Its reactions are slower, its tentacle strikes are marginally less precise. The swordfish slashes, lateral strikes of the blade aimed at the tentacles, not the mantle, not the beak, the tentacles. Disable the weapons first, cut the arms, reduce the threat, then close for the kill. The scars on the swordfish suggest that this strategy doesn't always go cleanly. Some swordfish carry dozens of sucker scars, each one a moment where the squid got close enough to grip. Each one a moment where the swordfish was fighting for its life in the dark, swinging a self-healing blade at an animal covered in razor-toothed suckers, in water cold enough to shut down any other predator on the planet. The swordfish wins these encounters. We know because the swordfish survives and the squid does not. But the cost is written on its skin in permanent circular scars that never fully heal. The gladiator's record. Every mark a battle, every battle conducted alone. Scientists examining the stomach contents of swordfish caught in deep, long-line fisheries have confirmed the diet. Giant squid beaks appear alongside the beaks of smaller cephalopods, fragments of mesopelagic fish, and occasionally crustacean remains. But the giant squid beaks are the significant ones. Each beak represents an encounter with an animal that fights back with 10 arms and 2 feeding tentacles, each one lined with suckers capable of gripping with enough force to leave permanent scars on a 450-kilogram predator. The swordfish doesn't hunt giant squid because they're easy. It hunts them because at 3,000 feet, in water too cold for any other large predator to function, the giant squid is the largest available prey, and the swordfish is the only predator equipped to take one on. The swordfish is fast. It is incredibly fast relative to its size. However, it is not as fast as legends claim. Popular sources often cite the swordfish's speed as 60 miles per hour. The actual figure, confirmed by biomechanical modeling and hydrodynamic analysis, is approximately 34 miles per hour. For a 450-kilogram animal, this is still an extraordinary speed. However, the reason for this speed limit is more interesting than the speed itself: cavitation. At very high speeds, the pressure on the trailing edges of the fish's fins and its body surface drops so rapidly that the water vaporizes. Tiny vacuum bubbles form in the low-pressure zones behind the fins. When these bubbles collapse, and they collapse violently, they emit shock waves that erode biological tissue. Water literally tears the animal apart from the outside. Cavitation is the reason marine propellers are designed with such precision. It is the reason torpedoes have speed limits. And it is the reason no fish in the ocean, no matter how much muscle power it possesses, can exceed approximately 34 miles per hour. The speed limit is not biological, it is physical. Water enforces it itself. The swordfish pushes as close to this limit as any animal can survive, and to do it, it uses one more adaptation that seems almost unfair. There is a gland at the base of the beak. This gland secretes a thin, continuous layer of oil onto the swordfish's skin. This oil reduces friction between the skin's surface and the surrounding water, enabling the animal to move through the ocean with hydrodynamic efficiency approaching theoretical limits. The swordfish self-lubricates. This oil is not a simple lipid layer. Chemical analysis of the secretion reveals a complex mixture of fatty acids and esters, specifically optimized to reduce surface tension in seawater. The composition is adjusted according to the salinity and viscosity of ocean water. This is a specially formulated lubricant produced by a biological gland that has refined its formula over millions of years. It glides through the water like a ghost within the oil, reaching speeds that would cause cavitation damage in any other animal of similar size. A self-healing blade, a brain furnace, glowing eyes, skin with reduced friction due to the oil, and a maximum speed that pushes the cavitation limit imposed by water's physical properties. The swordfish has evolved to reach the absolute limit of what biology can achieve in a fluid environment. However, there is a cost to engineering at the edge of physical limits, and the swordfish is paying that cost in full. The swordfish grows faster than nearly all other large vertebrates in the ocean. It reaches hundreds of kilograms in just a few years. Its growth rate is staggering. This rate is driven by the massive caloric intake required to power its heat-generating organ, daily deep dives, high-speed hunting, and the constant metabolic demands of maintaining a warm brain within a cold body. However, the energy cost of this lifestyle is unsustainable in the long term. The heat-generating organ operates 24 hours a day. The swordfish constantly expends energy, whether hunting, resting, or migrating. Deep dives deplete massive energy reserves, descending and ascending a mile multiple times a day, with a body weighing half a ton. The self-repairing swordfish requires constant cellular repair across its entire surface. The fat gland must produce fat non-stop. Every system in the swordfish operates at maximum capacity or near it at all times. There is no sleep mode. It runs until the machine breaks down, overheating in the process. The result is a short lifespan for such a large animal. The great white shark can live up to 70 years. Bluefin tuna can reach 40 years. The swordfish, however, dies within less than 15 years. Most don't even make it to 10 years old. A half-ton top predator with a self-healing weapon, a brain furnace, heating eyes, oil-coated skin, and the fastest lateral strike in the ocean, dies before reaching the age of a domestic dog. And it dies alone. Because the energy demands of the swordfish are so extreme that a single individual requires a vast hunting territory to sustain itself. Two swordfish in the same territory means insufficient food for both. They cannot tolerate the presence of their own kind. They live alone, they hunt alone. They migrate alone across entire ocean basins in total solitude. No pods, no pairs, no social structure of any kind. The most comprehensively engineered predator in the open ocean is also the loneliest. This metabolic intensity also explains one of the swordfish's most bizarre documented behaviors, attacking boats, ships, and, in at least one confirmed case, a research submarine. These are not defensive acts. The swordfish is not threatened by a vessel. The current explanation is metabolic desperation combined with the constant neurological arousal required to maintain the heater organ and sustain the daily deep dives. The animal is perpetually on the edge of exhaustion, perpetually hungry, perpetually processing sensory information at the maximum rate its heated brain allows. When a large object enters its territory, something that vaguely resembles a rival predator or an unusual stimulus, the swordfish strikes. Not because it's smart enough to attack a ship, because it's too wired to stop. The same engineering that makes it the perfect hunter also makes it a neurological live wire that cannot stand down. Bills have been found embedded in ship hulls, in whale carcasses, in submarine pressure housings, each one driven in by an animal that couldn't help itself. The end, when it comes, is not dramatic. As the years accumulate, parasites colonize the gills. Copepods, monogenian worms. They attach, multiply, and gradually obstruct the gill surface area that the swordfish depends on for oxygen exchange. The metabolic fire that powered the heater organ, the deep dives, and the high-speed hunts begins to dim. The heater organ cannot maintain its temperature differential. The eyes cool, the brain slows, the reflexes degrade. The swordfish that once slashed through schools of fish like a scythe, that dove a mile into the crushing dark every morning, that swung a self-healing blade at giant squid in the freezing void, that animal slows down. The cold that it held at bay for its entire life begins to seep in through the eyes, through the brain, through every system that depended on the furnace that is now failing. The abyss that the swordfish mastered for a decade finally claims it. Not through violence, not through predation, through the slow, quiet, inevitable failure of a machine that was built to run too hot for too long. Born with teeth, dies toothless. Born with scales, dies smooth. Born small enough to sit on a fingertip, dies as a half-ton ghost that has attacked submarines. The swordfish is born as a generic larva, indistinguishable from a million other fish larvae drifting in the plankton. Over the next few years, it deletes its own teeth, sheds its own scales, grows a meter-long blade from its skull, develops a furnace behind its eyes, fills its skin with oil, and becomes the only billfish on Earth that hunts in the crushing darkness of the deep ocean. It creates a weapon that absorbs its own shockwaves and repairs itself from layered bone. It heats its brain to a temperature 30 degrees higher than the freezing point of the water around it. It fights giant squids in complete darkness and uses a lateral cutting technique to neutralize them before they can grasp its tentacles. It lubricates its body to approach the cavitation speed limit as much as biology allows. It grows at an explosive rate, consumes its reserves at unsustainable rates, and dies alone within less than 15 years due to parasites blocking its gills and a malfunction in the heater behind its eyes.